Zeal Education Society, redefining excellence.
Hello students, in the previous video lecture of the basic electrical engineering, we have learned the mutual inductance, the definitions and numerical based on it. Now in this video lecture, we are going to learn the coefficient of coupling K and its importance. Now let us consider the two magnetically coupled coils having turns N1 and N2. Consider say these two coils are magnetically coupled having turns N1 and N2. Say their self-inductances are, let their self-inductances are L1 equal to N1 square upon S equal to N1 square upon L upon mu0 mu r A equal to mu0 mu r A into N1 square upon L, and L2 equal to N2 square upon S equal to mu0 mu r A N2 square upon L, where L is the length of magnetic path and S is the reluctance of the magnetic circuit. So the L1 equal to N1 square upon S, similarly L2 equal to N2 square upon S. These are the two self-inductances of the two considered coils. Let current flowing through the coil, first coil, say let I1 current flowing through coil 1 produces flux phi 1. Flux phi 1. This flux phi 1 equal to N1 I1 upon S. Suppose fraction K1 of this flux, suppose fraction K1 of this flux, that is K1 phi 1 links to coil 2, that is N2. Therefore, mutual inductance M equal to K1 phi 1, this links to N2, and this happens due to current I1. Now let us put the value of phi 1 here. So K1 N1 I1 upon S, and this K1 upon I1 into N2. So this I1 get cancelled and equal to K1 N1 N2 upon S, where S is the reluctance of the magnetic circuit. Similarly, let current I2 say current I2 produces the flux phi 2. Current I2 in coil 2 produces flux phi 2. Suppose fraction K2 of flux phi 2, that is K2 phi 2, links to coil 1, that is N1. Therefore, mutual inductance M equal to K2 phi 2, this links to N1 and this happens due to I2. Now putting this value, now here phi 2, the phi 2 equal to N2I2 upon S. Now put the value of phi 2 upon I2. So here it is K2 N1 N2 upon S. This is equation 2, this is equation 3. Now multiplying equation 1 and 2. M square equal to K1 K2 N1 square N2 square upon S. So K1 N1 N2 upon S, K2 N1 N2 upon S. So M equal to, take K, this is nothing but, or M square equal to K1 K2 L1 L2. Let K equal to square root of K1 K2. Therefore M equal to K square root of L1 L2. Therefore K equal to M upon square root of L1 L2. So this is the expression for coefficient of coupling. Note that K, K1 and K2 all less than 1. They are the fractions. Thus the coefficient of coupling can be defined as, it is the ratio of mutual inductance present between the two magnetically coupled coils to the square root of product of their self-inductances. So it is the ratio of mutual inductance present between two coils to the square root of product of their self-inductances. To the square root of product of their self-inductances. K equal to 1, coils are said to be tightly coupled. when K equal to 0, coils are said to be magnetically isolated. So in this way, we have finished the expression for coefficient of coupling K, and it is given by m divided by square root of K1 K square K equal to m divided by square root of L1 L2 and K equal to square root of K1 K2. Note that here coefficient of coupling K, then K1 and K2 all are always less than 1. Now when the coils are tightly coupled, there is no magnetic leakage at all. In actual practice, it is not possible without leakage. So still we can say K equal to 1 when coils are tightly coupled. That means there is no magnetic leakage. And when K equal to 0, coils are magnetically isolated. There is no relations between the two coils. The coils are placed remotely and therefore there is no connection in between them, and we can say the coefficient of coupling K equal to 0. So in this way we have finished this video. In the second video lecture we will see few numericals based on coefficient of coupling K. Thank you.